the light there. Hello, everyone. My name is Ajay Jacob, and I'm the Director of Projects at the California Dreams Hub. Today, I have the pleasure of introducing Professor S.J. Ben-Yu. He's a distinguished professor at the University of California at Davis. His research includes 2D, 3D photonic integration for AI and neuromorphic computing, 5G, 6G networking, RF-Photonic arbitrary waveform generation, LiDAR, EW, and the future internet. He is currently leading the 3D EPIC AI project at the Northwest AI Hub under the DoDMA Commons program. Prior to joining UC Davis in 1999, he was a senior research scientist at Bellcore, leading technical efforts in integrated photonics, optical networking, and system integration. His research activities at Bellcore included the next generation internet, reconfigurable multi-wavelength optical networks, wavelength interchanging cross connects, wavelength converters, vertical cavity lasers, and high-speed modulators. Professor Yu received his BS, MS, and PhD from Stanford University and is a fellow of IEEE and Optica. He is a recipient of the DARPA Award for Sustained Excellence, the Bellcore CEO Award, the Mid-Career Research Faculty Award, the Senior Faculty Research Award, and numerous Best Paper Awards from the IEEE, ACM, and the Optica Conference. And I have the pleasure of introducing him. He's going to give the talk today on RF-Photonic arbitrary optical waveform generation and measurements for future 5G, 6G, EW, and LiDARs. Welcome, Professor Ben. The stage is yours.
Great. Thanks so much, AJ, for a very kind introduction. And I met some of you in person last week at the USCISI, and I'm honored to give this talk today, RF-Photonic arbitrary waveforms and measurement for future 5G, 6G, EW, LiDARs. So the question for you today is, can we generate arbitrary waveforms of any shape in phase and amplitude with theoretically infinite record length? You can have just infinite amount of information that prolongs across more than terahertz bandwidth. Once you generate such a waveform or waveforms, can you measure them? Can you measure arbitrary waveforms of any amplitude phase shape with infinite record length of larger than terahertz bandwidth? Can you use such technology in a real network, elastic optical network? And then can you actually use this to make a 5G, 6G elastic network? In fact, it'll be an elastic RF optical network for 5G, 6G on top of elastic optical networking that interfaces seamlessly. Can you use that technology or technologies for EW, radar, and LiDAR, as well as 5G, 6G? So these are kind of the questions I have, and hopefully we have a lot of good discussions on this topic. It goes back to 1980s when my colleague, Professor John Heritage and the team looked into this optical wave that has hundreds of terahertz bandwidth in principle. And he was actually playing with this, this waveform in the spectral domain, not in the time domain. So basically you decompose into many spectral components and then impose, in this case, phase modulation or phase features on each one spectral component, and then assemble the waveform together. And he found that the waveform gets reshaped. In fact, by using Fourier transform, you can actually design the waveform you want to put as output. But then that is called basically the beginning of optical CDMA, where if this was a repeated waveform, repetition in the frequency domain does not have anything to do with the size of the pixels you use here. But what's interesting is that if you actually impose that time domain, frequency domain comm lines that will consist the time domain waveform, and then if you manipulate the waveform on each line-by-line basis with amplitude and phase, you can actually shape the waveform. In this case, you actually purposely flatten the phase and kept the amplitude to be about the, say, sync function. And you can actually get the sync time domain waveform, super Gaussian of the form. And then if you decide to put quadratic features of the phase on a line-by-line basis, you can actually generate kind of a chirped waveform. So that's kind of nice, but it's a little bit boring, right? Because if the pulses come out, multiple pulses come out, then each pulse will be shaped with a certain shape they are repeating. So then can we make this to be infinite record length? And the way to do this is to go back to the same idea, but impose the dynamic phase and amplitude modulation on each comb line. So here, the optical frequency comb, the coherent lines of comb lines that are basically modular lasers or some time and phase amplitude correlation between them. In the time domain, it can look like pulses that will repeat at the time scale that is inverse of this frequency channel spacing. If you demultiplex into line by line, each line will have basically CW line shape. But if you impose phase and amplitude on each one of those frequency components and then put them together, then even though each one of those amplitude phase modulation can be, let's say, 10 gigahertz with a 20 gigahertz waveform, you can actually create terahertz bandwidth waveform, even though, again, if the electronic modulation is limited in the bandwidth, by synthesis, we can create a waveform that's arbitrary. In fact, arbitrary in terms of phase and amplitude across the entire spectrum of the frequency comb. And in this case, if you have certain waveform you like to generate in the time domain, in the phase and amplitude, you can Fourier transform, inverse Fourier transform, and impose them on each frequency component and unambiguously figure out what amplitude and phase modulation you want to apply, except that instead of amplitude and phase, because the phase actually repeats itself 2 pi, and you cannot really infinitely modulate 10 pi and 100 pi and so on, you'll be actually doing this as an IQ modulation with analog. So then you can think of reasonable CMOS drivers, let's say D2A, A to D with limited bandwidth, to create the arbitrary waveform that can cover terahertz bandwidth or more of arbitrary waveform. In fact, for telecom, we were actually using this for, say, communicating between data centers with 16 QAM. Over here, you can do 64 QAM or amplitude modulation. You can do anything you like. In fact, this becomes kind of a new way of coherent communication. If I look at this again in the how we're doing this, as I mentioned, in the time domain, you may have transform limited optical pulses coming in. And in the frequency domain, that may appear to be very nice low noise comb lines that are coherently locked to each other, and then separate them in using DMUX, and then use IQ modulator driven by, say, D2A, perhaps with the amplifier. Then each one of those lines will be broadened with the phase and amplitude pattern in the frequency domain. And then you will synthesize this waveform. It's okay to have overlap. In fact, that actually helps you. And then create the synthesized waveform of arbitrary phase and amplitude, which can be Fourier transformed into time domain and achieve unambiguous waveform in the time domain. And so then basically utilizing the low bandwidth modulators and low bandwidth, perhaps CMOS electronics, you can generate the arbitrary waveform that covers terahertz bandwidth and beyond. And typically what we use here is a high contrast DMOS and then purposely overlapping passbands for continuous waveform and so on. Kind of the algorithm we developed, we basically divide and conquer. We divide the target waveform. If you have certain target waveform you want to generate in time domain with the amplitude and phase, and then you basically Fourier transform into target spectrum with the phase and amplitude, and then you slice them and then figure out what waveform you should generate on each slice understanding that there will be a overlap, and this overlap will be again coherent because you started off with the coherent comb. So this will be the waveform you want to generate in the spectral domain, which will be transformed time domain, so you can figure out what kind of time domain per waveform do you have. If you continuously modulate this in the time domain in the IQ, then you, in principle, you have an infinite record length, infinitely lasting arbitrary waveform, but you'll be limited by the amount of memory that in practice in your PC and so on. Another thing we do is that our spectral filters have some shapes. For instance, here there's a gap there. So we purposely pre-emphasize, and this pre-emphasis can be done by IQ modulator. We can purposely have the IQ modulator to have certain pre-emphasis here in the IQ modulator. And this is preferred. We don't prefer amplitude phase, as I said. Phase modulators can be useful, but you cannot continuously ramp up the phase to 2 pi, 3 pi, 10 pi, and so on. So we'll use IQ modulators driven by D2A converters and so on. So this is kind of the waveform we generated. It's kind of one of the first dynamic waveforms we generated. And for the optical communications, we tried on-off keying, DPSK, and then we actually also were able to dispersion compensate ahead of time, ahead of the fiber transmission and so on. The bandwidth is terabit per terahertz, so we could actually put 1.2 terabit per second, 16 QAM. But as I said, our electrical arbitrary waveform generators were limited by the number of bits here with 16 channels. In this case, I think we chose 32 channels. And then the target and measured looked pretty good in terms of the our initial testing of 1.2 terabit per second. And then this is kind of an example of temporal waveform that apply to presumably infinite record length modulation, and we can generate the time domain waveform that looks kind of arbitrary, and we can basically go on and on if you have an infinite amount of memory and so on. In the spectral domain, the Fourier transform can show waveforms like this. In terms of technology, our initial technology was using indium phosphide. The reason we used indium phosphide was because we actually had fairly good way to do etching and regrow. We used the HVP regrowth for hydride vapor epitaxy to do planarization and so on. And then, so we were able to make the very, very high resolution, 10 gigahertz resolution, 100 channel. And then the each one of those phase arm had amplitude and phase modulation, not because we want to do dynamic modulation, but we want to actually make sure that if there's any imperfection in terms of phase error or amplitude error, we could actually correct for that by putting Mach Zehnders here. And then over here, we had a high-speed modulation. And in this particular case, we used the reflection mode. So the comb will come in and get modulated, and comb waveform will come out and so on. And this is our indium phosphide chip. And we actually use the optical interconnect to use the optical modulation, induce the phase and amplitude modulation on these things. And then now we're doing this with the RF-Photonic and so on. But the waveform, the OAWG looked very good, had 17 dB extinction. And as I said, some amount of extinction limitation can be overcome because these comb lines are all coherent. We can actually modulate them and correct them by applying the correct waveform on each one of those comb lines. And then we'll show you the silicon nitride and silicon-based waveforms later on. In terms of technology, we need optical frequency comb. You can use mode-lock lasers. What's actually convenient is that if you do electro-optic amplitude phase modulation, with the modulator you can perhaps purchase, typically you can buy dual Mach Zehnder modulator. In our case, we have the modulator with the phase modulator included. So if you have a very good single frequency laser waveform coming in, the initial phase modulation will give you Bessel function. So it will give you Broadcom, but it will have Bessel waveform amplitude. But if you follow with the dual electrode Mach-Zehnder modulator with amplitude and delay control, so it's not equal amplitude on both arms, and then also bias control it, then with this single stage, we can actually get fairly good uniform 32-line frequency comb. And the reason this is very useful is that you have a full control over central wavelength and also frequency spacing. So we can actually have AWG-R-based OAWG that can be tailored or by using the frequency tuning and RF tuning, you can actually map to that. You can actually use the nonlinear fiber-based broadening to easily create maybe 175 lines. And then if you follow up with the additional stage with the dispersion shifted, dispersion decreasing fiber with the EDFA, then you can actually generate more than 1,000 lines. Typically, you don't need 1,000 lines. With the 32 lines or 100 lines, you can do quite a bit of very nice things, including 5G, 6G networking, and so on. So then the next thing is that, well, are there ways to do this without chewing up RF power? So what we did was that collaborate with OAWG that generate, OAWG has Q of billion, the resonator that are machined to have high Q up to billion and beyond. And then my group has designed the prism coupler that is on the waveguide, silicon nitride waveguide, so we can actually integrate the resonator on the chip. And then in this OAWG package, there's a DFB laser. And thanks to a small amount of relay scattered resonant diffraction, the DFB laser will be self-injection locked. So this, I believe this was the first self-injection locked comb generation with integrated photonics, although we have not integrated monolithically the resonators yet, and there are new papers from NIST and Santa Barbara who achieved these things. NIST actually has new generation of photonic crystal resonators. We are collaborating with them, and they can generate dark and bright combs and solitons. In this case, both achieves thousands of lines. Or you can actually focus on more flattened waveforms with those. And what I hear and what we are collaborating them on, you can get 65% or even higher optical to optical power conversion efficiency. The noise is very, very low in both cases, minus 160 dBc per hertz. In the OAWG case, the noise is actually lower because Q is actually higher and so on. Quite exciting with stable comb, low noise. They can actually support low noise RF-Photonic and so on. Now, the one thing I mentioned to you is that you may have to shape the waveform with modulation, but there may be easier way to do this. If the AWG has this kind of comb by line spectral shape, you can actually use this RF filter, but perhaps you can make an RF filter that will repeat at the same 10 gigahertz or 20 gigahertz spacing so that one filter can correct for hundreds of comb lines shaping. So that's where the RF-Photonic unit cell FIR, IIR lattice filter comes in. If you, as you know, in the electrical FIR, IR filter, you have RLC that repeats itself. In the optics, you can have optical coupler and optical delay line that can repeat itself. So the shape of each unit cell are the same, but then each unit cell can have different coupling, different phase delay, and then you can create the FIR using this technique. On the other hand, if you actually have a resonator, you can actually have infinite impulse response filter, and you can again cascade them. What we have done was to actually fabricate this, what may look like infinite impulse response filter, but put the phase shifter on each one of these components. So if you shift the phase correctly, you may actually make this to be completely 100% coupled. That may look like a lattice filter with the delta L, or the different length there. So single device with the tunable coupler can support FIR or IIR depending on the coupling strength that we can tune. In addition, we can tune the resonance of the resonator to change the phase. That will be the zero pole shifting. And then you can shift the phase arm on the Mach Zehnder lower arm to shift the zero. So each lattice filter provides zero and pole. And you can have the pole to vanish if you actually have 100% coupling in the coupler. So that'll be a kind of a same shape of unit cell that can support both the IIR and the FIR. And just like in the case of digital filter, you can actually create many zeros and poles that will be cascaded to create many different kinds of filters, including Butterworth filters and notch filters and so on. So in our case, we used our own fab, but also used the foundry on the same design, and used the at least the 4-unit cell. So then you can actually see 4-unit cell here, 4-unit cell here, and then the single unit cell. And then we fabricated them with the different designs. And then for this project, DARPA required that we do switching at the nanosecond speed. So we actually use the carrier injection as well as electro-optic depletion mode and so on, even though we could have actually gotten thermo-optical phase shifter as well. We had to make this absolutely low loss with the AW coupling so that we can cascade these things at multiple stages. So the result here is that we looked at input on the arm, the port number 1A, and then looked at the output on port number 2A and 2B. So looking at the frequency domain, you see H12 response, which will be input 1A to output 2B. Also H11 response, that will be input 1A to output 2A. In the time domain, the resonance you see here is a function of the resonance, which was designed to be, in this case, 10 gigahertz free spectral range to match the 10 gigahertz AWG-R, the AWG DMUX that we had. In the time domain, by tuning each one of those, in this case, PIN diode on-slip photonics to, in this case, inject the carrier, to inject the carrier at maybe 5 milliamp, 1 milliamp, 0.6 milliamp. By tuning these 5 tuning elements, you can move the poles and zeros based on what you desire and so on. And then you can create this corresponding time domain H12 as well as time domain H11. And you can see that in certain combination of current level, you can make it look like a notch filter. We can make it look like 3D third order Butterworth filter and so on. We actually get about 80 dB dynamic range with the reasonable input power, thanks to coherent detection and so on we're using and so on. So that's basically kind of the OAWG. And then DARPA got really excited and then said, hey, if you can measure arbitrary waveform in terahertz bandwidth, how are you going to measure arbitrary waveform with a terahertz bandwidth? And we're kind of puzzled about it. And my students are much smarter than me. And they said, oh, Professor Yu, you taught this class 239A, and you said receivers are inverse of the, basically mirror image of the transmitter. I say, aha. So then instead of having COM lines going in with the IQ modulation driven by IQ analog driven by CMOS D2A, generating waveform slices and synthesizing, and then generating arbitrary waveform, you can actually do the opposite, propagate this backward and then do slice by slice coherent detection, where you have full wave quadrature balance detection. So you actually have you can measure I and Q unambiguously, just like you have applied I and Q with D2A, but then over here, you can put A to D. So by the action of COM lines going in with and then waveform going in, you can actually recover the spectral component of each one of those spectral component. I'd like to also emphasize the fact that the COM here and COM there can be completely independent. In fact, we have done the experiment 10 gigahertz COM and 20 gigahertz COM, or we have done the experiment with the distance way beyond coherence length of the COM. We're able to recover the waveform unambiguously. So kind of zooming into this side, it basically is that full wave full optical hybrids that will basically create the spectral slices based on spectral demux. And then they will mix the COM lines on a line-by-line basis. And then they'll give you coherent balance detector output that can allow you to measure in-phase and quadrature part of each spectral component. And then once you do that, using your digital synthesis or whatever you have to synthesize the waveform in the time domain and the spectral domain. What's really exciting about this technique is because you're using coherent detection with a very, very high quality optical frequency COM. In principle, this can be nearly single photon detection. We typically can go down to about 10 photon detection. So then here we attenuate the input beam down to, in this case, 150 attojoule per pulse shot. So it's almost like a single shot detection. Actually, it is a single shot detection of amplitude phase measurement. And we're able to recover these things in the time domain and the frequency domain. You can actually see that the waveforms has very high fidelity, even if you have reduced the power level from 10 femtojoule to 150 attojoule. Power level is amazingly, to your eye, it looks very, very linear. In fact, we have done up to like 80 dB linearity measurements. Now, as I mentioned, we could actually use this for fiber transmission, and you can have a receiver in Japan, receiver transmitter in principle in San Francisco. You can have completely different COM generation and OAWG or EWM, and we're able to recover the waveform in the time domain and the frequency domain. And this is actually a 400 gigahertz waveform with more than terabit per second information. So, we have been working on now silicon photonic based integrated OAWG, OAWM. So then if you have a COM source does not have to be on the same chip, but let's say you have a COM source on the same chip, then you can demux the COM line and impose IQ modulation with perhaps on-chip or flip-chip bonded CMOS D2A converters with digital data. And then have that IQ modulated spectral slices to be combined by the multiplexer and this waveform coming out. And in fact, as I said, we have done this with indium phosphide based and also silicon based chips are over here. When the waveform comes back from optical network, you can actually demux them, create the spectral slices, and on the slice by slice, coherent detection can allow you to recover I and Q component of the waveform in the electrical domain, and then you can synthesize the waveform to re-synthesize the terahertz waveform. And this is our kind of one of the silicon photonic based chips that we've been using. So I know that today's talk is mostly RF-Photonic and ERON, the 5G, 6G, millimeter wave, and so on. So we're going to shift gears. What we have done was to attach antenna on these devices so that instead of we do fiber optical communication, what we call elastic optical networking. we can now start to use elastic RF optical networking, where we can actually put this antenna over here with the appropriate amplifier, and then A to D, D to A, maybe just, in this case, maybe we just get rid of D to A, but linear amplifier, modulate the IQ modulators, and then provide high fidelity signals. You can also put antennas here, or you can also put the antennas on the receiving end. I'm sorry, the transmitter end. So then this output can transmit millimeter wave, and so we're going to talk about that. From the commercial viewpoint, that'll be exciting for the creating a smart city 5G 6G network, not just the 5G 6G. Currently, 5G 6G has horrendous amount of latency, but if you use a optical network like I've mentioned with the OAWG, OAWM, you can actually interface your 5G 6G seamlessly because it's a coherent optical to coherent RF network. And then for DoD, we can think about 5G 6G networking, that the more kind of low side rate and power, more mobile, and then have the the millimeter wave antenna and so on. Now, this is a very busy slide. I'm going to go into one by one. So as I mentioned, we may have an optical network that is based on this OAWG or OAWM, and then we can distribute these waveforms, and then at the RAU, you can actually have a COM9 or COM9s, so that you can decide to basically generate slice of OAWG to create, let's say you want to have a carrier frequency at 100 gigahertz or 20 gigahertz and so on. So basically heterodyne will give you RF waveform, and that can actually, in fact, if you use MIMO, you can actually have even more bandwidth. You can have n times the information bandwidth if you use MIMO with the additional channels and so on, especially division. But then other RAU may use different or the same spacing, so that it can be 20 gigahertz or 100 gigahertz. So this spacing of this COM line can define the RF COM here. And then that can be basically looking like something like this with unicarrier detectors with millimeter antenna. You can beam shape those. I'm going to talk more in detail a little bit later on. And then on the receiving end, you may have antenna that will create the amplification with IQ, and then you can interface with the optical elastic optical networking. So as I promised, I'm going to dive into this part. So elastic optical network here, you have a terahertz bandwidth, and the terahertz bandwidth, you can actually decide to have certain slice of waveform to go to RAU1 or RAU2, and RAU1 can use the same kind of carrier frequency, or you can use different carrier frequency. It's kind of, there are many different ways of doing it. But the point is that terahertz bandwidth on the optical network can be distributed to RAU with the total flexibility, so to speak. And then if you do in the single RAU, if you decide to use spatial division multiplexing, let's say in this case, 4 antennas, then you can actually have 4 different pieces of information in the local area network, RN, and then have those 4 different pieces of information go to 4 different destinations with the independent information content. So it's completely flexible, elastic. You can put any waveform, any protocol, any modulation format you like that applies to both optical and electrical. What's also exciting is that because the optical network itself is an elastic optical network, the RF network also becomes elastic RF optical network and can support a lot of multiple terahertz piece of information that can be distributed to multiple RF network and so on. Then the transmitter itself, as I mentioned, you may have that ODU providing CRAM-based edge node DSP, and then modulate IQ. The same thing I mentioned already is that this is OAWG, dynamic OAWG. But in this case, you can decide to send different spectral bands, like I mentioned here. different spectral bands going to split different RAUs, and different RAU may decide to use the optical frequency comb, maybe use multiple of them or one of them or whatever you like to do, but generate either space division multiplex-based MIMO or whatever. But here, what we do here is to do beam shaping. So beam shaping by optically beam shaping, digital optical beam shaping, to apply different RF phase using the optical phase shifting. And then you can actually avoid using terahertz amplifiers or millimeter wave amplifiers by using unitravel carrier photodetectors have amazingly good efficiency, close to 50%, and going out to multiple of 100 gigahertz bandwidth. And then you can have a short antenna that will be driven by each one of those. And then you can beam shape, beam form. You can have MIMO-based multiple beams, or maybe more concentrated and so on. And then you can have multiple of those things based on the protocol I mentioned. Okay, so that's the transmitter side. On the receiving end, you will have the same kind of beamforming idea, except that you may have waveform coming in from here, then it will create a different kind of a phase front, right? That will be mixed by the local oscillator driven by optical frequency comb. And then that will be modulating each one of those IQ modulators. And then you put the optical frequency comb to synthesize the waveform to basically generate the waveform that can be put together for upstream and so on. So this is kind of the receiving end. And here you can put LNA and HPA with the modulator, or you can have the mixer. There are many different options exist. So that's basically a 5G, 6G, but I want to shift gears now. It's already 12:38. The last topic that I mentioned was a LiDAR. With the OAWG and in fact LiDAR and radar, the OAWG that I mentioned can actually have one or multiple comb lines can basically go from one spectral size, tune it, and hand over to another spectral frequency and so on. That the IQ modulator has a full capability to do singleton generation. But perhaps there's a better way to do this. So then perhaps there is, once you do demultiplexer of comb lines, instead of doing IQ modulation, maybe you can do frequency shifting modulation on each one of them. And that might be easier. And you can also have multiple of these comb lines modulated at the same time. So if I look at my textbook, when I was in grad school, I was seeing this and intrigued by it. If you come in with optical wave, single frequency optical wave that has the, in this case, clockwise circular wave, right-hand circular wave. And then if you have a half-wave plate that can rotate, and let's say you rotate at the frequency F in the same direction, then what comes out is also right-hand circular polarized light, but it will have the frequency shifting. If that rotates at the same direction, you actually have downshifting by 2F. If you actually go the other direction, if you upshift by 2F, this is actually not new. This is actually my textbook, my homework by my graduate course, but Crane has invented this, so to speak. So I was asking my student, how about if we do this? Can my student rotate these things very fast? Then we can actually upshift or downshift the waveform. Actually, I'm sorry, the right-hand circular right-hand. So the polarity changes because of halfway plate, but you're rotating this at a relatively high frequency. But if you want to do this with the millimeter wave, rotation becomes challenging, right? Who can rotate this at the 100 gigahertz type of stuff? But mathematically, this looks beautifully. You know, left-hand circular polarized wave, right-hand circular wave. If you rotate at the omega r, then you actually have right-hand circular polarized wave with the frequency shifting. And the nice thing about this is that you can also work this as an optical isolator. This kind of a side story. So then we looked at the lithium niobate, and by looking at the crystal symmetry, and one choice is to use R22 component with the Z propagation. And then using R22 with that modulation, you can actually generate, you will find that you can actually generate the circular polarized light if you have a two-piston engine, two-cylinder motorcycle, and one motorcycle will modulate the three electrode based biasing with the horizontal E field. But then for the other wave, you actually modulate with vertical E field. So basically a superposition of sine wave and cosine wave with a phase retardation, so that this right wave will have some understanding that the wave plate is rotating clockwise or counterclockwise by changing the phase of this. That's basically the same thing what the two-cylinder engine is doing. If you have a motorcycle, you may have a single cylinder, but if you have two-cylinder, you can actually have this guy to rotate at cosine omega t, and then this guy to rotate at cosine omega t times, say, 45 degrees or something. So then you can actually start to have some sense of rotation, but if you change the phase, then you can rotate in the other direction. So that allows you to upshift or downshift the frequency. And this is actually experiment we've done. So simulation-wise, this was very singleton. There's no side tone. IQ modulation with a singleton, single sideband, very difficult to make very clean. But if you have a purely halfway plate type of waveform that is rotating with the harmonic, with no harmonic distortion, you can expect to have upshift or downshift without spurious sidebands. And this was the actual experimental measurement. And then we could also generate down conversion or up conversion by changing the phase and so on. So that's kind of the LiDAR and radar. And there are a lot of things we're doing. We have demonstrated this RF ERON network experimentally. We have done a lot of digital signals processing based control network and built the kind of the whole system and testbed, including EON and ERON. And we're looking into some really interesting experiments utilizing those with the real scenario. And by collaborating with you, I hope that there are a lot of opportunities. I think dynamic, not just any OAWG, but dynamic OAWG, OAWM gives a EON opportunity. We can make a high fidelity EON transmitter, OAWG transmitter, OAWM transmitters. But then by using coherence of those EON, OAWG, OAWM with the heterodyne, you can actually start to use RF-Photonic optical network using the dynamic OAWG, OAWM, basically coherent optical network to coherent RF network. And if you remember the MIMO and STM, we're using temporal, spectral, spatial domain coding. There's actually fairly sophisticated coding we're using. And a lot of technologies we're using are RF photonics, going all the way to terahertz photonics using multiple cones. We are doing beam steering with the MIMO, OAWG, ERON, and then there's ERON 5G, 6G transceivers. And then in terms of our networking protocol and so on, we have a software-defined ERON OAWG 5G, 6G network. I'd like to acknowledge my team. All the work is done by my students, and they are great. They come up with really nice ideas, and we've been supported by a lot of sponsors. We appreciate them quite a bit. And when I was there at the USCISI last week, we had a lot of good discussions, and I currently am looking for a 5G, 6G team that we like to work on, because we're on the university side. And if there's a team that I can join or support, or if there's a collaborator I can work with, I'd be very interested in collaborating on the topic one, integrated sensing and communication, because our OAWG, OAWM with the RF-Photonics can support 5G, 6G network, as well as radar and any RF sensing as well. So with that, I'd like to thank again for this opportunity and appreciate it. Thanks so much.
Thank you, Professor Ben. It was a great talk. I will open up now for questions. Any questions from the audience? It seems there are no questions from the audience. I do have a couple of questions, Professor Ben. You know, when you so you showed one chip where you have both the multiplexers and demultiplexers.
Right.
And how did you come around the noise? You know, I mean, the phase noise or crosstalk that you would probably be introducing when both the multiplexers and demultiplexers are on the same chip. How did you do that?
Okay, that's a very good question. As usual, AJ asks a lot of good questions. I think the nice thing is that this is an integrated chip. So then you would actually imagine almost no frequency that you may have some vibration and so on. So the integrated chip, you would expect really no noise there. But then if you're worried about this overlap of the waveform that may create the coherence here, but it's actually intended to overlap so that when you do OAWG or OAWM, this overlap is actually good. In some sense, if you have a waveform that was generated from this COM line that generate waveform, say, signal over here, and then this COM line generating from this COM line generating waveform here, these are supposed to be coherently mixing together to generate a total waveform. So you do have to worry about the phase noise bit of the line to line. You do have to worry about any vibration or some phase fluctuation between the waveguide, which is kind of negligible for integrated chip. Then you don't really have to worry about the noise from that issue. But if you do this experiment with the fibers and fibers to just vibrate and phase and so on, then you have to worry about the noise like that.
Okay.
So to answer your question again, we actually did system analysis and say what happens if you drive this with say 12 ENOP on each line with very quiet optical frequency you can get. What is the system-wide terahertz band ENOP? It turned out that we can get very, very close to 12 ENOP because optical frequency is very, very quiet and so on.
So since you mentioned about 12 ENOP, so how did you manage the synchronization between the driver electric? So you probably had the electronic driver signals, right? How did you manage that synchronization? Or you did not have to do that?
I have to ask my students, but as far as I know, we had OAWG that had multiple channels, electrical OAWG that had multiple channels, and we drove them together, and we measured up to in terms of simulation, we have done up to 12 ENOP, but for this experiment, we have done up to like 6 ENOP because the instrument was limited. If we use different instrument, we can probably do experiment 12 ENOP. So you're right that there may be some phase noise induced. If you have electronic phase noise here, electronic phase noise there, that may create phase noise at the stitching. So we have to worry about that. But currently, so in terms of simulation, we're able to get up to 12 ENOPs.
Okay. And I also think you also talked about reconfigurability here, right? So if you have to reconfigure this, what is the time scale that you're talking about, like milliseconds, or what's the time with which you can do that reconfiguration of the modulator signals?
Right. So we were in the middle of building a FPGA system that does the DSP and then creating with the high-speed modulation and so on. But did you say synchronization or the latency? Okay, right.
Yeah, the latency.
The DSP latency is there. So we did not quite measure this. We're not as keen on measuring the latency from that. But if we don't use FPGA, we can record 120 bit into the electrical AWG with multiple channels and run it at very high speed. There, the latency was measurably very, very low, but that's also instrument limited. In the real scenario, I would imagine that the antenna that is driving LNA, driving high power amplifier, going here directly, if we do not have any DSP, I would imagine that the latency is basically speed of light. You know, how fast can the antenna trigger these things? If the wires are short, the latency should be below 10 nanoseconds.
Oh, latency should be below 10 nanosecond. I was thinking of
right. Because we're
worst case millisecond, best case microsecond is what I was thinking. You say nanosecond. Okay.
Well, if you do, that's right. If you do use the DSP, it can be many microseconds. But if you're talking about the ERON, the RF 5G 6G wave coming in to drive the antenna, that will drive the HP, the low noise amplifier, high power amplifier, and then modulate on the COM, then that's basically speed of electrical transmission line and speed of optical wave, and that can be made below 10 nanoseconds.
Okay. Any other questions from the audience? Oh, there is a question here. There are two questions coming up. Could you please, this is from Sung, CY Sung. CY Sung, do you want to take the mic and ask the question? You have two questions here.
Yeah.
Okay, so
the first question is about the electronics, the latency, how that impact to your optical signal.
And I think on that question I just answered. If you don't use DSP, if you only use analog amplifier to drive the IQ modulator with the analog signal, then there is the latency of electrical signal propagating through the electrical wire and amplifier that can be negligible, and optical wave propagating. So I would say you can make it below 10 nanosecond latency. But if you use DSP, you'll be limited by DSP latency to many microseconds. And then the second question, CY, so does the temperature invariant factors impact the OAWG system? So the currently we're using indium phosphide or silicon-based OAWG chip. So the whatever temperature drift you may have, it will affect the same way. You have to worry about the phase difference between arm number 1, arm number 2, and so on. But if they're all moving up and down, temperature changing at the same time, same uniform temperature, then that effect is negligible. But we do have to worry about DMUX and MUX. DMUX and MUX, if the temperature changes the frequency band, and if the COM lines are not moving, then you may have effect due to that. But fortunately, currently we do have athermal AWGs. So using athermal AWGs, we can actually minimize the temperature effect. Other environmental effect may be vibration, but because this is integrated photonics, my understanding is that vibration will not affect the quality of the OAWG or OAWM signal.
Thank you so much. Thank you.
But CY, it has been a while. If you can email me, we can start the chat. Yeah.
Sure. Yeah, I'd love to. Thank you.
I have one more question. This is with respect to, since you showed interest in the ISAC project, and you also discussed about the 12-bit ENOB, Professor Ben. I was wondering, how does this 12-bit ENOB translate to the ISAC performance? You have both sensing and communication there.
Right.
And it's a multi-bit problem. Yeah. But you also talk about the reconfigurability also.
Right. So again, very, very nice question. So when you generate this waveform, right, you want to actually generate as high fidelity D2A or analog signal as possible. So if you have a 12-bit D2A, you can have 4096 levels of analog, right, for the I and Q. So typically, we generate this waveform with 5.5D, and then we can still generate fairly nice waveforms and so on. But then with the 12 ENOB-based driver, you can actually get much better fidelity waveform. We actually do OAWG, OAWM, and correct the waveform. If you use 12-bit based waveform generation, waveform measurement, and correction, you can actually get much better result. So that's the fidelity. In some sense, you can put, we talk about how much information you can put in the bandwidth. So spectral efficiency, how much bit per symbol, is a function of how much ENOB is there. If you just do on-off modulation, you can barely get 1 bit or half bit per symbol. But if you have 4096, in principle, you can have 12 bit per symbol and so on. But then another is that the I and Q, you can actually have another 12 bit per symbol on the I side and Q side. For the measurement of the very weak signal, like radar-based sensing, I think that ENOB is very, very important because you may have a large noise background. So you may have the low noise amplifier, high power amplifier, followed by optical. And then when you do that, just like I said, if you have a good A to D, D to A with 12-bit ENOB and so on, that'll be very, very helpful.
Great. Thank you, Professor Ben. I think it is now the hour, closer to 4 o'clock. Thank you once again. And Amy, you could put your slides. This is the technical seminar slide for the next week, which is, okay, here you can, if you want, you can register here to get updates on the technical seminar. The next week, it will be Robert Heath from UCSD giving the talk, and looking forward for the next week's presentation. And once again, thank you, Professor Ben.
Thank you so much.